Hello, so this video will cover our NAE Grand Challenge topic, which is providing clean access of water to communities. Now, one of the main issues with this challenge and what makes it a challenge itself is that the already developed systems, such as desalination plants that exist, are very costly. So problem one is that it's costly and inefficient energy-wise in the process of providing access of water to freshwater depleted areas. Now, our goal, or what my group members and I have come up with as one of the most effective ways to combat this problem, is for engineers to come together to create small-scale systems. Now, these small-scale systems are typically very inexpensive and efficient as opposed to the already existent large-scale systems that exist. They're inefficient in two aspects. Inefficient in the fact that they will be able to provide clean access of water to a lot of people at a very low cost, and that not a lot of energy is typically lost through these developed systems, such as with desalination plants, where a lot of energy is required for water to be cleaned, and not a lot of water is actually cleaned through the energy input to the system. This has been an issue and it remains one, and we believe that through the development of these systems by the collaboration of engineers that we could be one step closer to solving this problem. So our data set that relates to this and our code that we have established through our data set deals with a water filtration system. Now, this water filtration system consists of channels. There are layers, and the nanochannel has water molecules pass through it in order to be decontaminated. The dataset provided to us shows water molecules, 300 specific water molecules at different time steps in which they are evaluated, and it gives us the x and y velocities of these water molecules respectively. So each column represents the x and y velocities at a time step, and you can see that over here through our data set key. The velocities are measured in nanometers per second. So we go back to our code, we go to our algorithm, and it says that our objective is to identify the x and y velocities of 300 water molecules found across 4 different time steps. These time steps would be 87,000, 87,500, 88,000, and 88,500. We will be displaying the maximum, minimum, and average values of the magnitude of velocity. So our known for this algorithm would be the data set that I have already shown, which would be columns A through H of this Excel file, which provides us with the x and y velocities respectively at each time step. So the first 2 columns would represent one time step, the next 2 columns would represent one time step, and so on. Going back to the algorithm, we see that our unknown is the minimum, maximum, and the average magnitudes of the velocity at the particular time steps that we have chosen to evaluate, which would be 87,000 to 88,500 in increments of 500. The assumptions that we have made is that the minimum velocity can be found by using the built-in function min on MATLAB. The maximum velocity can be found by using the built-in function max, and finally the average velocity can be found using the built-in function mean. So these built-in functions in MATLAB will allow us to solve for the values that we hope to obtain from this data set provided. The start of our algorithm would be to set all values of the x and y velocities into their own variables. Now, in order to do that, we will have to go back to our code. Our code is over here, so I'm going to expand this script. And and we want to import the data from our Excel file onto our command window, which can be done through xlsread. So I'm going to run this section and exit this out since it is for later. And I pull up my command screen to have all of the x and y velocities displayed for us in their same column. However, A, B, C, D is not listed for us to be able to decipher which column it is. But we do know that the first two columns would represent time step 87,500, and the next two columns would increase in increments of 500. And we know that the x and y velocities are listed respectively and in that order. So in order to set these values of one column into a variable, what we would have to do is take the variable time step, which reads our data, and which is of itself a matrix, considering that there are both rows and columns involved. And we will take that variable and set it next to parentheses that reads colon, comma, and a particular column value. The colon means that all of the row values will be displayed for us at the column given as the next value. So we would be doing this for the next 8 columns, as you can see over here. Going back to our algorithm, we see that the next step is to find the magnitude of the velocities at each time step. Now, the magnitude deals with the x component and the y component of the velocity, and it is represented over here on this painting document. The x component of the velocity is shown here along the x-axis, and the y component of the velocity is shown here along the y-axis. Taking the magnitude of this velocity altogether, we would take the square of the y component and the x component, and we would add them together, and ultimately take the square root to find the magnitude of the velocity. And this is represented in our function listed over here, in which we use different variables to show that the x velocities squared plus the y velocities squared would equal a particular variable, and that particular variable having the square root taken of it will give us the magnitude. However, for our code, we decided to use the built-in function magnitude to have MATLAB do it for us, since essentially one of our main aims in creating this is for it to be useful for engineers in analyzing future data sets, so that it will be more simple and less complicated on the user themselves. So going back to our algorithm, let's go to our test case since we're at about just the time to where this becomes relevant. We will be evaluating time step 88,000. So going to our code, we see that time step 88,000 would be this over here, considering that it goes from 87,500, and 88,000. Since we have decided to take the magnitude as A, B, C, C1 over here would represent the magnitude at 88,000. So C1 over here would represent our magnitude values, in which the x and y are taken and combined into magnitudes. So for our new values, we will have 4 time steps or 4 columns displayed separately instead of individual columns displaying the x and y velocities. Scrolling down, our next objective is to find the minimum and maximum values of the magnitude of the velocity for 4 different time steps. So in order to find the maximum or the minimum values, we would have to use the built-in functions max and min, and in order to find the location in which they are placed, we use 2 variables within brackets, and the second variable would represent the location that it is placed according to the row. So if we want to evaluate time step 88,000, we go to C1, in which we placed our own special variables t and y to represent the maximum value and the location in which the maximum value is placed, and T1 to represent the minimum value in that location. And then we would run this section again so that our T1, Y1 are displayed for us over here. So T, which would be our maximum value, would be 2.175, and that would be located for us at row 283. And we scroll down for C2, which would be the Y velocity evaluated, and it says that 0.1587 would be the minimum value, and that it'll be located at row 60. Okay, scrolling down through our code, this is the process that is repeated since we are evaluating 4 different time steps. So it will be repetitive, but it will be a good way for engineers to have a good idea of evaluating the velocities of the water molecules and having more data sets to compare it to. So although the process is repetitive, it is a way for engineers or interpreters to better understand the process of what is going on, since they need more feedback from it. So scrolling down, our next objective is to find the mean values or the average values of the magnitude of the velocity at the different time steps, and this will be found through the built-in user function mean. Going to our algorithm, it says that over here as our step to find the average value of the magnitude at each time step. So we would be doing that over here by using mean and then giving the magnitude variable A1, B1, C1, D1, and so on. If you want to find the average value at C1, which is what we are evaluating at the moment, we have to run the section again. And it lets us know that the average value is 1.3715. Okay, now we have just about covered the basics of our code, and we are going to the more important part of it, which provides the user with the menu option to choose the time steps of the water velocity to analyze. So it has the individual time steps listed over here, as well as a graph for them to view all the time steps and all of the specific parts of the graph, parts of the data that we are analyzing, like the minimum, maximum, and average, and it provides us with a table to read that data. So this would be option 1, 2, 3, 4, 5, 6, or more specifically, that is how MATLAB reads them. So we created conditionals for this part of our code, in which J1 would give us an output that would read the minimum, maximum, and average values at time step 87,000, and J2 would do the same for 87,500, J3 would be the same. So we're going to run our section to test the data for 88,000, since that is the time step we are analyzing. And our menu option pops up. So we're going to click that we're going to analyze time step 88,000. And at the very end of our command window, it lists to us that the maximum value of 2.2 nanometers per second, the minimum value of 0.16 nanometers per second, and the average value of 1.37 nanometers per second was found for the magnitude of the velocity of water in time step 88,000. So it reads to us everything that we need to know for that time step. But if we want a better picture of what is going on, we would run this section, and instead of choosing any of the time steps, we would choose graph. In just a moment, it will pop up. Now the graph shows us the minimum values at each time step, the maximum values at each time step, and the average values at each time step. And what we used for this particular option is Polyfit to display the line of best fit for all of these point values. which can be seen over here for option 5. We used polyfit for the minimum, the maximum, and the average, so that we would have a line of best fit for those, and so the plot would be better visualized for whoever decides to analyze the data. So the very last option, which is option 6, we will run the section and choose that for the table to be displayed to us. And as you can see through the table, the average velocity at each time step is listed, as well as the minimum velocity and the maximum velocity. And this concludes our process of allowing the user to analyze the data given to them through this menu option. Okay, scrolling down, the very last part of our code is to find the highest average velocity of the water, the absolute maximum velocity of the water, and the absolute minimum velocity of the water at any time step. We can see through this table that the highest average velocity is obviously this, and that the lowest average minimum velocity is obviously this, and the highest maximum velocity is obviously this. But in order to simplify the process, we want MATLAB to find this for us. So we will take all of the values and set them up as a matrix, all of the maximum values, set them up as a matrix, and we will use max again to find the absolute maximum, and we will use max for all of the average values to find the absolute maximum average, and then we will find minimum to find the absolute minimum value. Going back to our code, we see that this was the last part of our algorithm, finding the absolute min and max and the highest mean value. For our test case, we already have seen that we use the built-in min, max, and mean functions to solve for the values, and that the maximum value was displayed, the minimum value, as well as the average value was displayed for time step 88,000 given by our code. Altogether, our code should be very beneficial to engineers in that it provides them with a lot of different tools to interpret the data. Along with giving them the data set itself to look at, which is shown over here, and giving them an option of what part of the data to analyze, such as the different time steps, as well as giving them an option of the graph or the table, the engineer themselves can use the graph, for instance, to decide what is the highest maximum value or the lowest minimum value, which would be this over here. Looking at this, we can assume that the highest maximum value would be 2.6 or something similar to that. And given by our final fprintf statement, it says just that. So when we go back to our graph, we see that the average value is listed in between the maximum and the minimum values, and that is very logically backed, considering that the average should be somewhere between those two values for each time step. And this further validates the data given to us, and that it is accurate and logically backed. In the case of the table, we can also use the table to go and to validate the data given to us by our graphs. So it gives us the specific values that we may have estimated in our mind through looking at the graphs. And this is all very useful to engineers. All of this is used as a process of validation, and that is why the process in our code was repetitive, so that engineers will be given the opportunity to look thoroughly through the data sets given to them and to be able to come up with rationally based conclusions on any pattern going on through any system, and this particular system being a water filtration one. The limitations, however, of this code, or of this in particular, is that we only listed the 4 time steps rather than 26. Now, it would have taken a lot more time to do so, But given that any engineer that looks through this should have a good idea of how to repeat the process so that the 26 time steps will be evaluated, it will give them a clear idea of how to do so on their own. There are many limitations that exist through any code. Nothing is absolute or extremely perfect, but our code made an attempt of giving the user a good idea of the water molecules through time steps. And we hope that datasets such as this will be useful to engineers in the future and to ourselves in the continuation of this course.